Okay, let's get started. So, inner product spaces. Right? So, 5.4 inner product spaces. Okay, so remember, right, what an inner product should do. So we have some vector space, right, and we have on it, we hope to create on it a binary operation, right? And the binary operation has to satisfy three conditions, right? That if you take the operation of a vector against itself, you always get something bigger than 0, right, for all v and p. And further, this thing should equal 0 only when the vector is the 0 vector. 2, we want the operation to be commutative. Right? And 3, we want the operation to be linear in the first variable. So it's called inner product. If these three things happen. Now, this you have already from last time. Okay. So now, why don't we require linearity in the second variable? Or do we have linearity in the second variable? Copy. Yes, Anna.
You remember the second condition where it's x, y equal to y, x.
Yeah.
Then if you just apply that to the third one.
Yes, exactly. So the thing is that we don't need to require linearity in the second variable because the operation is commutative, right? So these two and 3 together imply that it's commutative in the second variable, right? Because if you had this expression in the second variable, well, you just commute it to the first variable and it's linear there. Okay. So we actually do have linearity in the second variable automatically. Okay, and so let's last time we start off with one example. Let me put a bunch of examples. First is the obvious one, Rn, with the dot product given by taking the transpose of the first guy and the matrix multiplying it by the second guy. Right? In other words, the standard dot product. So that's fine. That certainly is a dot product, right? It's linear, it's commutative, and we always, when we take the magnitude of something, we always get something greater than 0. And if you take the magnitude of the 0 vector, you get 0. And if the magnitude is 0, then it's the 0 vector. Right? That certainly satisfies all the conditions. Number 2, a modification of that. Actually, let me call it 1 prime. So V in Rn, and you have some W in Rn with Wi bigger than 0 for all I. And we define our inner product. We define another inner product by taking the old dot product and throwing these W's into the mix. Okay. So we multiply, we have these products here, but we multiply each one by Wi, and then we add all these things, add all those things together. Okay. So this is a weighted inner product, right? Weighted this is the old dot product that you know, but we've thrown in a weight, right? Some of the dimensions are emphasized more than others. Okay. Is it commutative? Kathleen, do you have a question?
Oh, no, sorry.
No, okay. Is it commutative? If we change the order, does it matter? No, it doesn't matter. It's commutative, right? If we take alpha x plus, is it linear? It's still linear, right? What about this? If we take something against itself, do you get something positive? Right? If you take x against x, what are you going to get? You're going to get summation xi squared wi. Is that positive? Sure, because the wi's are all positive, right? So you're going to get a sum of, you're going to get again a sum of positive things, right? Suppose you get 0. Suppose you get, certainly if you take the 0 vector and you take the magnitude with respect to this weighted dot product, then you get 0. But what about the opposite? If you get 0, does that mean that the xi must have all been 0? Yeah. Right, so let's look at it, right? If, let's say that this xi, so xi squared wi equals 1 to n equals 0, right? So last, checking part 1, right? If xx equals 0, then what does that tell you? Then all the xi must have been 0, right? That's the only way this can happen, right? All xi are 0, right? So yeah. So this being 0, the magnitude being 0 with respect to this inner product does force the vector to be 0. Okay. What if I did this? Is it still an inner product?
What did you do?
Sorry? What if I did this? Is it still an inner product? The answer is no. Some people are nodding like this. The answer is no, right? Because you could suppose, like, well, to be kind of pathological about it, let's suppose that we take all the wi's to be 0, right? Then this being the norm being 0 wouldn't mean that these are 0, because in fact you'd always get 0 for everything. Right? Okay, so yeah, so we actually do need this thing to be strictly positive for this to work out as an inner product. Okay. Example 2. A, B are m by n matrices, and you could take an inner product on the space of matrices by just defining the dot product over all entries. Okay. This is really no different from example 1, right? This is just, treating this thing as one long vector, right? Treating these matrices as one long vector. It's not particularly interesting. One that we saw last time. B is the continuous functions on AB. And we let the dot product be defined as the integral from A to B of the product of the functions. You could introduce a 3 prime for some w continuous function such that the function is positive everywhere, you could let fg be the integral from a to b of the weighted integral. Right, so that actually would also work as an inner product. Last time we saw that this guy works as an inner product. The weighted version of it also works as an inner product. Last example, number 4. B is the polynomials of degree less than n. And we're going to define a sort of peculiar dot product on it. So choose n points, x1, x2, through xn in Rn. Okay. And define the dot product of two polynomials as the sum of p against q at each of those points. Sorry, this should be R, not Rn. Okay. So this is kind of funny, right? You have, you choose, you choose some points, right? You choose some points, x1 through xn, and then you define your dot product as I'm going to evaluate each polynomial, right? So you have some polynomial, you have some other polynomial, right? You evaluate the polynomials at those points, and you take the products of those values, right? Products of those values, and you add them all together. And that's going to be your dot product. Okay. Okay, so let's think about this. Is this a dot product? Well, certainly, 2 and 3 are, again, easily satisfied. So the hard one is, as before, it's 1, right? So is it true that if we take a polynomial against itself, we always get something bigger than equal to 0? Sure, right? Because we're just going to get a sum of squares, right? So it'll be bigger than equal to 0, right? If we take 0, of course, we're going to get the dot product of it against itself as 0. But what about the opposite, the hard one? Suppose you take the dot product against itself and you get 0. Does that force the polynomial to be 0? To be the 0 polynomial? So let's check it. Say that summation pxi squared, I from 1 to n, is 0. Does that imply that p is the 0 vector? P is the zero polynomial? Yes, why? Elena?
Because when you square anything, it's going to be greater than or equal to 0, and so the only way for the sum of that to be 0 is if they're all 0.
Okay, so they're all 0. So p of xi is 0. So at each of those points, the value of the polynomial must be 0. Okay. But we want to say that the polynomial is the 0 polynomial. All you've said so far is that it's 0 at these n points. Why must it be the 0 polynomial? Anyone know the answer? It's a polynomial of degree n, right?
Does it have to be continuous? Oh, no.
It's guaranteed to be continuous. It's a polynomial. But anyone see it? So think of say we're in P3. So polynomials of degree less than 3, and it's 0 at these 3 points. Notice we have a parabola, and it's 0 at 3 points.
So we're parabola with time at 3 points?
Yes. Right.
So if it goes through all 3, then it has to be 0.
It has to be a flat line. It has to be constant. Right. So, right, the polynomial is of degree n minus 1. Right. It's an degree n minus 1 polynomial, and it has n zeros. Right. The only way that can happen is if it's 0 everywhere. Right. Because in polynomial of degree n minus 1, right, unless it's a 0 polynomial, it will have at most n minus 1 zeros. Right. A quadratic function has only 2 zeros, unless it's 0 everywhere. Right. A cubic has only 3 zeros. Right. A cubic has only 3 zeros. Parabola has only 2 zeros, unless it's 0 everywhere. Okay. So yeah. So in fact, this oddly defined guy is also an inner product on an inner product. So we've made an inner product space out of it. Is it okay? Question? Any questions? Questions? Okay. Okay. So these are all examples of inner product spaces. Once we have an inner product, then you can define orthogonality. So, right, just in the normal way, we've got U and V inner product spaces, and U and V in V and inner product space. If the inner product is zero, we say U and V are orthogonal. So, in say the continuous functions on 1, 1, then 1 and x, right? The inner product of 1 against x is you integrate 1 against x, right? And you get 0. So the function 1 and the function x are orthogonal to each other. Right? 1 is orthogonal to x in C11, C-1, 1. Okay. Another definition, right? You have, again, if you have inner products, then you can define the notion of magnitude or norm, right? So V in V and inner product space again. You define the norm of V by norm of V is defined as the inner product of the function of the thing against itself to the 1/2. Okay. So, right, like in the above example, right, the norm of 1 is the square root of 2. Okay. There's some properties that inner product spaces have that are just like the properties that Euclidean space has. And here's an example of the first one, the Pythagorean theorem. So again, V and inner product space, and U, V, in V. If U is perpendicular to V, then U squared plus V squared equals V squared. Oops. This one here. Okay, so there's, you know, in any inner product space, you have a Pythagorean theorem, and the proof is as follows. You say, well, look, if I look at u plus v squared, that's just u plus v plus v. Right, and then use your properties of inner products. Right, this is going to be u plus uv plus vu plus vv. Right, put these guys at 0 by orthogonality, and that's the end. So any inner product space has a Pythagorean theorem. Right? So for example, right back here, these guys are perpendicular to each other, right? Right? 1 and x are perpendicular to each other, so I know that the magnitude of 1 plus x is the same thing as the magnitude of 1 squared. Is that of x squared? This is the sort of thing that's going to hold because these guys are perpendicular to each other. Okay. Okay. So there's Pythagorean theorem. Any questions? It's pretty. As you see, the proof is just relies on the properties of inner products. Okay, the second thing, second property of inner product spaces is the Cauchy-Schwartz inequality. Okay, so remember what the Cauchy-Schwartz inequality said. So that if you have two vectors, then the magnitude of the dot product was less than or equal to the product of the magnitudes, right? That's the Cauchy-Schwartz inequality. And you remember, does anyone remember how we got it? How we got this? Yeah,
you use the dot product being like magnitude of 1 and
Yeah.
the other cosine theta.
Yeah. So we use the geometric interpretation of the Euclidean dot product, right? The dot product was the product of the magnitudes times the cosine of the angle between them, and the cosine, the magnitude of the cosine is less than 1, so that gives us this. Okay, but we don't have that here, right? We don't have that geometric interpretation here. However, we still have a Cauchy-Schwartz inequality. So it'll take a little bit of work to get there. Okay, so not that much. It's pretty straightforward. So oh, actually, there's a second part to the Cauchy-Schwartz inequality. The part that one always forgets. Further, equality holds if and only if u and v are linearly dependent. Okay. So if you get that these things are equal, then you know that one guy is a multiple of the other guy. Yeah.
Never mind. Never mind.
Okay, good. You answered your question? Very good. yeah, when I was an undergraduate, I almost never spoke to my professors. Rather, I'd have some question, and then I'd go over to my professor's office. And at Princeton, it's this tower. So there's this tower on the edge of campus, and you go to the tower, and it's silent in the tower. And you go up into the tower, and for me, I'd like sit outside of my professor's office, just thinking, and then I'd answer the question, and I'd go back. So yeah, I rarely spoke to them. Okay. Yeah. So the proof of this requires two lemmas. So lemmas, or maybe I think the proper expression is lemmata, but we're going to say lemmas. Like errors, errata, stigma, stigmata. Lemma, lemata. So here are the lemmas. Say that v is not equal to 0, and that u and v are in V and inner product space, and that P is the projection of U onto V. And now I realize that I forgot to give you the definition of the projection. So I'm going to put it over here. So this is another thing that you get. We define the vector projection of U onto V by the projection is the dot product, this inner product of U against V over the inner product of V against V times V. And we define the scalar projection as UV, as just that is this. Okay, so we're just using the, this is a straight generalization of the Euclidean definition, right? This is how you define it in the Euclidean sense. Both of these are how you define the projections in Euclidean space. So. Okay. So, right. So. You have some U, you have some V, right? P is the projection. P is the projection of U onto V. Okay? Except that this picture doesn't exist, right? This is a Euclidean space picture for something that is not Euclidean space. Okay, so this is just something to keep in mind. Okay, so blah blah blah. You have these vectors. Then one. U minus the projection of U on V is perpendicular to the projection of U on V. Okay, and that's just an easy calculation, right? Right. You want to see that U minus the projection of U on V, that's UV over V, excuse me, times exactly that equals 0. And you see how that works, I think, right? The first one, you get u against this thing here, so you get uv over vv times uv. Right? So that's the first thing, and then minus uv vv right? And so you get something minus itself is 0. Right? These things cancel, and you get this minus itself is 0. Okay, so it's just elementary school or junior high school or something. Okay. It's just distribution. Okay. I'm going to erase this. Okay. Part 2. Okay. So u equals the projection of u on v if and only if u equals beta v for some beta. U equals the projection of v. U is equal to its projection if and only if u is some multiple of v. Okay, so why is this true? Right? Well, if u is the projection of u on v, then why is u some multiple of v? This is just true by...
Because they're in the same direction, so...
Yeah, basically. Right? I mean, this is basically by definition. Right? If u is the projection of u on v, that means that u is this thing. Right? In other words, u is some multiple of v. The end. Okay, so this is the first part is just by construction, right? True by construction. Right. That's how we define the projection. The projection is this particular multiple of v. Okay. Backwards, also easy. Suppose that you say that u equals some multiple of v. Does that guarantee that u will be equal to its projection onto v? Well, let's see. Then the projection of u onto v is going to be u v over vv times v. Right? Which is beta v. Right? So, which is u. Right? So the projection of u onto v is actually u. So just a calculation. Sorry. Just can't work on my back here. I have to remind myself to stand up straighter. Look cocky, arrogant.
Power pose.
Power pose. I don't like it. I stand like this. I don't like it. The Japanese, I was saying, the Hulk with power hides its talons.
With fire?
With power.
Oh.
The Hulk
Oh,
with power.
I was real confused back here.
Yeah, the Hulk with ability, basically. The Hulk with ability hides its talons. Not to say that I have any talents. Okay. So there's this lemma, right? And this lemma has two things which are pretty straightforward. Okay, but we'll use them to get the Cauchy-Schwartz inequality. Okay. So here we go. Proof of Cauchy-Schwarz. Okay. So first note. If V is a zero vector, then we're done. So we don't have to worry about V being the zero vector. And if V is a zero vector, then this is certainly true. Right? So let's assume that V is not the zero vector. Okay, and let's think. We want to show that this thing is smaller than this thing. Right? Now these guys are all positive, so that's actually equivalent to showing that their squares are less than the squares. Right? Since A is less than B, if and only if A squared is less than B squared when A and B are positive. Right? If A is less than B, then certainly A squared is less than B squared, and if A squared is less than B squared, then A is less than B. As long as we're dealing with positive things. Okay, so, but that is equivalent to saying that UV over the magnitude of V, quantity squared, is less than the magnitude of U squared. Right? But look at what this thing is, right? This thing is the magnitude of the projection. Right? Remember what the projection was, right? The projection was U, V, 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 right? That's to say U, V, magnitude of V, magnitude of V, V, right? And so, right, so the magnitude of the projection, right, this is a unit vector right here, right? The magnitude of the projection of U onto V, right? The magnitude of the projection squared is that thing there. So really what we're asking, what the Cauchy-Schwartz inequality is saying is that, can you show that the magnitude of the projection squared is less than the magnitude of the thing squared, right? So this is some P where P is the projection of U on V. magnitude of the projection squared plus u minus the projection squared equals the magnitude of u squared, right, by the Pythagorean theorem. So by Pythagorean theorem says that this is true. Yeah, Mia.
What does this? Does it say P is equal to the projection of
Yeah.
U?
Projection of V onto U.
Okay. Projection of V onto U or of U onto V?
U onto V. Excuse me. Okay, so we're trying to show that the size of the projection is smaller than the norm of the projection squared is smaller than the norm of the thing it's squared, right? But right, what we have here is that u minus the projection is perpendicular to the projection, right? U minus the projection is perpendicular to projection, and so by Pythagorean theorem, right? Pythagorean theorem says that if these guys are perpendicular, then we know that p squared plus plus u minus p squared is equal to u squared. Right? A squared plus b squared is equal to c squared. Okay. So what does that tell you, right? But right. And we're trying to show that this thing is smaller than this thing, right? But we know that this thing plus something else is equal to this thing, right? So certainly it's going to be smaller than or equal to, right? Because this plus this, this positive number plus this positive number equals this positive number. So we know that this thing is indeed less than or equal to u squared and equals it, and they are equal if and only if u minus p squared is 0. Right? That is, if and only if right? If and only if u equals some multiple of v, or some beta, right? That is, if and only if they are linearly dependent. Right? So that's everything gets done in one move. So this is how the proof of the Cauchy-Schwartz theorem goes. Right? It's basically just realizing that what the Cauchy-Schwartz theorem says is something about projections. Right? You didn't notice it. Maybe you did notice it. You might have noticed it before. But what it's really saying is this: that the size of the projection is smaller than. The size of the projection of u onto v is smaller than or equal to the size of u, right? And then we invoke the Pythagorean theorem, right? Just to say that in fact the size of the projection plus something else is this squared plus this squared is this u squared, right? And so that shows you that. So all this, the Cauchy-Schwartz is actually an immediate consequence of the Pythagorean theorem, which is a consequence of just inner products, of having an inner product, of the properties of inner products. Any questions on how this goes? Okay, so let me just close up with one last thing. So then, now that we have a Cauchy-Schwartz inequality, what we see is that so then we know that the magnitude, right? So in any inner product space V, if you have two vectors in V, then this thing, the magnitude, the size of the and this thing is less than or equal to 1. Right? That's what Cauchy-Schwartz tells you. So you always get a number between 1 and -1 when you take the dot product of two vectors and divide by the products of the magnitudes. Okay. So this allows us to define angles in any inner product space. Right? We define the angle between U and B to be the arc cosine of U against V over the product of the magnitudes. Okay, so you can talk about angles between functions. So this basically, having an inner product on a space allows you to put some notion of geometry on the space. So, yeah, there's a little bit left in this section about norms. I guess we'll talk about it. I'll either ask you to read it by yourself. It's not that hard. I'll either ask you to read it by yourself, or we'll talk about it on Monday. So, okay, that's it.